All right, good morning, everybody. So yesterday we talked about introduction to the atom. We talked about Bohr diagrams. We talked a little bit about Lewis dot diagrams. We'll continue our conversation with Lewis dot diagrams today. We're going to talk about the periodic table and trends in the periodic table. So what happens as we go from left to right within a period? What happens as we go from top to bottom? And how does that affect the different characteristics of an atom, particularly its size? So the first thing we need to do is we need to talk about the structure of the atom again. So we'll take an example. Let's say, let's talk about carbon. So I have a carbon atom. And carbon has an atomic number of 6, so it has 6 protons. And it has an atomic mass of 12. So if it has 6 protons and each proton weighs 1 atomic unit, and the whole thing weighs 12 atomic units, then it must also have 6 neutrons. And we know that electrons don't weigh anything, or they weigh so little that it doesn't matter. So we just need the same number of electrons as we have protons, so that the negative electrons balance the positive protons. So we have 6 electrons. And we know that only 2 electrons fit in the very first orbit, and then we have up to 8 in the next orbit. So we're going to have 2 in that first orbit, and then we're going to have 1, 2, 3, 4 in the next one. So we have 6 and 6, we have 6 electrons, and everything's balanced and everything's happy. When things bond, and we're going to talk about ionic bonding a little later on. When things bond, it's a matter of the sharing or the stealing of electrons. So atoms will either lose or gain electrons depending on the size of the atom and depending on the characteristics of the atom. And what really happens is electrons like to be in a state where they have a full valence shell, which means atoms like to have the maximum number of electrons on their outside orbit. So we talked yesterday, we have the first orbit can hold 2 electrons, the second orbit can hold 8, and then the third orbit can also hold 8. So if an atom has 2 electrons in its first orbit, and that's all it has, it's pretty happy, because it has the maximum number of electrons that it can on its very outside orbit. If an atom has 2, then it wants 8 electrons on its outside orbit to be happy. And if it has 3, it would want 8 on the third one also. So we'll go into more detail about binding and the role of electrons later on in the course. What I really want to discuss now is periodic table trends, and specifically we're going to talk about atomic radius, we're going to talk about electronegativity, atomic ionization energy, and electron affinity. So let's focus on atomic radius. And the atomic radius is the size of the atom right across the electron cloud. So that would be the size of the atom from here to here. And let's discuss what happens to the size of the atom as we move around the periodic table. So moving up, this is the first 20 atoms on the periodic table. It's blank. Let's start drawing what we know. So we know that this is hydrogen. And hydrogen only has 1 electron shell, and on that shell it only has one electron. And I'm going to start drawing electrons as dots, just because it's a lot easier than drawing those little E's. And the next one is going to be helium. But let's not worry about helium for now. We know helium has one valence orbit, or one reverse shell with 2 electrons on that shell. But let's go right down to lithium. So lithium has, it's the third electron, or it's the third atom in the periodic table, so it has 3 electrons. We can fit 2 on the very first shell, because there's a maximum of 2 on the first shell. And now we have to draw another shell. We have to draw another orbit here, and then we're going to plop 1 electron on that one. And then 4, 5, 6, 7, 8, 9, 10. Let's go to 11. 11 is going to be sodium. Sodium is the 11th atom on the periodic table, so it has 11 protons. And then if it has 11 protons, then it must have 11 electrons. And we know that the filling order is the first shell has 2 electrons, the second shell has 8, and then the third shell has 8 as well. So there would be 2 on its first shell, 8 on its second shell, that's 10. So we need to draw 3 shells. This would have 3. 2 on that one, 8 on that one, and 1 on the outside. So we have 2 electrons on the inside. 1, 2, 3, 4, 5, 6, 7, 8 on that one. And then we have 1 right outside here. So, what we should notice is, as we move down in the group, every successive atom has 1 more orbital, or 1 more shell in the atom that came before. So every time we move down within a group, we're adding an orbital. We're adding an orbit. And because we're adding an orbit, we're actually increasing the size of that atom. So in terms of atomic radius, the trend is, as we move from the top to the bottom, atomic radius increases. So it increases from top to bottom. What we should also notice is, within a group, every single atom has the same number of valence electrons. If we look only at its outside orbit, every outside orbit of the atoms within this first group all only have 1 electron in their valence shell. So every atom within a group has the same number of valence electrons. Not the same number of orbits, but it has the same number of valence electrons. So, as we go from top to bottom within a group, the atomic radius increases, but all the atoms within a group share the same number of valence electrons. Atomic radius as we go from left to right in the period. So we would think that as we go from left to right in the period, we're going to increase the number of electrons and the number of protons and the number of neutrons. But the thing you need to know is the number of protons and neutrons in the nucleus. Because the nucleus is so incredibly small. Remember we talked yesterday, if it was the size of a football field, if the whole atom was the size of a football field, the nucleus would be a fly landed right in the middle. Like, the nucleus is so incredibly tiny in terms of appearance, you wouldn't even be able to see it. So the size of the nucleus doesn't affect the size of the atom. It's mostly the size, or the orbits that are affecting the size of the atom, and the affinity for the protons to attract its electrons. So if we think about a magnet, we have a magnet here, and then we have a magnet down here. And they're attracted to each other. They want to get to each other. the size of the magnet, let's say that this one is positive and this one's negative, the size of the magnet, or the size of the negative and positive charge of the magnet, will affect how strongly they're attracted to each other. If I increase the magnetism of the positive magnet and the magnetism of the negative magnet, they will be attracted with a greater force than if they were smaller. And the larger the magnets, the more they're going to be attracted to each other. And the same exists when we're talking about protons and electrons. The more protons we have, the more strongly they're going to be attracted by the electrons. And the more electrons we have, the more strongly they're going to be attracted to the protons, because electrons are negative, protons are positive, and they're going to be attracted to each other because opposites attract. So if I add protons and I add electrons, that attractive force is going to increase. It's going to get stronger. And we call that electronegativity or electron affinity. So the more protons we have in the nucleus, the more strongly they're going to attract the electrons that are in the electron cloud or the electron orbits. And as we go from left to right in a period, we increase the number of protons and increase the number of electrons. So we have lithium, and then we're going to have beryllium. So then we have beryllium here. And beryllium, now I'm going to start only drawing the electrons in the valence shell. So I'm going to be using what we call the Lewis dot diagrams, which only draws the valence electrons, because it's the valence electrons that are in charge of binding and bonding and the characteristics of an atom. So beryllium is the second atom in the period. Lithium had one valence electron in its outside shell, so beryllium is going to have two because it has one extra proton and one extra electron than lithium did. And as I move on, I'm going to go on to boron, which is going to have an extra proton and an extra electron from beryllium, so it's going to have 3 electrons. And then I'm going to move to carbon, which has 4. And then I'm going to move to nitrogen, which has 1, 2, 3, 4. And now that I have a 5th one, I'm just going to start pairing them up like that. Oxygen, so it has 6, 1, 2, 3, 4, 5, 6. And then we have fluorine, which has 7. And then we have neon, which has 8. And because as we go from left to right in a period, we have more protons inside these atoms and more electrons on the outside, the strength with which they attract each other gets stronger. And because neon is attracting its electrons more strongly than lithium did, we actually see a decrease in the size of the atom. So the atoms over here are actually going to be smaller because everything's being pulled in tighter. So if I were to draw neon, so we have neon here, and let's draw it with its first orbit and its second orbit, and it's going to keep its orbits in really close because it's really attracting in those electrons. So the first orbit has 2 electrons, and the outside one has, neon is the 10th atom. So it's going to have 2 on the inside and 8 on the outside for a total of 10. 1, 2, 3, 4, 5, 6, 7, 8. And it's going to hold those in really, really tight. Whereas lithium, on the other hand, doesn't hold on to them quite so tight. So let's draw lithium. And let's draw it out here. So lithium out here, and I'm going to have my first orbit. Let's redo that. And then I'm going to have my second orbit out here. Okay. So I have 2 electrons on my first orbit, and because lithium is the third atom on the periodic table, it only has 3 electrons and 3 protons, so it's only 1 out here. And because there's not as many protons and electrons, the attractive force between them isn't as strong, so lithium is actually going to be a larger atom than neon, which is further down the period. It has the same number of shells, but it's further down the period. So lithium will be a larger atom than neon. So as we go from left to right on a period, the atomic radius decreases, which is sort of counterintuitive because we would think the more subatomic particles there are, the larger the atom is, but that's not really the case. It is when we go from the top to the bottom of the group, but it's not the case when we're moving from left to right within the period. So let's summarize it on here. So atomic radius as we go from left to right, the general trend, and of course it's chemistry so there's always exceptions, but the general trend is that it decreases. But as we go from top to bottom within a group, because every successive atom within the group has 1 extra electron orbit, and electron orbits, they negate the effect of having an increased number of protons and electrons. Adding an actual orbit to the atom increases the radius so greatly that even though there are more protons and more electrons to be attracted, it still increases the radius of the atom. It supersedes it. It increases here. Okay. So that's atomic radius. Let's review the characteristics of groups and periods. So every atom within a group, same number of valence electrons. So all atoms within a group contain the same number of valence electrons. And of course, there are exceptions, but for the most part, and for our cases, especially in grade 9 chemistry, it's a very convenient way to think about it. So all the atoms within this group, so let's say group 17 here, fluorine, chlorine, they're all going to have the same number of valence electrons. Group 1, they all have 1, they all have 2. This rule does start to break down as we get to the 3rd and 4th periods of the periodic table, but for our intents and purposes, this is the way we're going to think about it until we start exploring the later periods next year in grade 10. Now, all atoms within a period have the same number of orbits. So hydrogen contains 1 orbit and 1 electron. Helium also contains 1 orbit and 2 electrons. So hydrogen is 1 orbit, 1 electron. Helium is 1 orbit and 2 electrons. And because the first orbit can only fit 2 electrons max, as soon as we get to lithium, now we have to start drawing 2. So we have 2 electrons on the first, 1 electron on the second. Beryllium will have 2 valence electrons or 2 electrons on its outside shell. Boron will have 3, 4, 5, 6, 7, 8, and neon will have a full outside shell, what we call a full octet. Octet meaning 8 electrons. But all of these atoms within the period have the same number of electron orbits. They all have 2. So the first period has 1 electron orbit, the second period has 2, the third has 3, the fourth has 4, 5, 6, 7, so the 7th would have 7. So if we're talking about francium, which is this bottom atom right here, we would have to draw 7 orbits. And as you can see, doing Bohr-Rutherford diagrams like this starts to get unwieldy after a while, because 1, 2, 3, 4, 5, that's still only 5. It just doesn't make sense to draw all the orbits. And because the electrons that aren't on the valence shell don't really affect the bonding characteristics of the atom, it's nice just to use the Lewis dot diagram and just draw the one valence electron. Okay, so all groups contain the same number of valence electrons. All atoms within a group contain the same number of valence electrons. All atoms within a period, all atoms have the same number of electron orbits. Okay. I think we'll end there. I'll answer a couple questions that people have asked, but I don't want to go too deep into periodic table stuff. We're going to explore more of that next week. We're also going to talk a little bit about binding, and then I think that's going to be mostly it for the chemistry unit. I think we're going to start moving forward onto electricity in about a week or so. But I'll post this up. I apologize about the audio. I'll put the closed captioning on, and if you guys have any more questions, definitely ask me. Or you can even ask me now if you're in here, if you want to ask on the YouTube chat. A few questions that came up about the periodic web quest. So a couple people asked me questions about metalloids. Metalloids are pretty special. So it's this, if you haven't gotten to the web quest, it's this question right here. Metalloids are pretty special in that they have characteristics of both metals and nonmetals, which makes them extremely useful for a very particular set of commercial uses. I kind of want you to research it a little bit, but they kind of give it away with semiconductors. Semiconductors are not amazing conductors of electricity. When we use heavy wiring for electrical conduction, for example, when you work in industrial applications or even in film, we use very thick copper wires because copper is a very good conductor of electricity. But when we talk about our electronics, like our phones and our tablets and our TVs, we don't want the metals that we use to be too conductive because it makes it very difficult. So a semiconductor is exactly that. Semiconductors are metals that can conduct electricity, but not as well as most of the metals. So there's some resistance. Everything conducts electricity a little bit, just some things conduct it a lot better than others. Obviously metals conduct electricity very well. Things like rubber don't conduct electricity very well. That's why rubber is an insulator. Rubber can protect us from electrical current. A lot of people, because you're in a car when you're driving and it has rubber tires, if there's an electrical current on the ground or an electrical wire has broken, you typically won't feel the electrical current because you're protected by the rubber in the tires. A lot of tools that are made have rubber handles. It's partly because the rubber handle is more comfortable, but also because the rubber protects you from the electrical current. So if we look at the periodic table, let's go down here. These are pretty much our nonmetals, and they don't conduct electricity very well. In fact, they conduct electricity so poorly that they basically don't conduct electricity at all. And these atoms right here, all these metals, conduct electricity very, very well. So these are great conductors of electricity. It happens extremely fast. If there's an electrical current through any of these atoms or through any of these materials, it's going to shock you very quickly. These are very poor conductors of electricity. We have a special name for those. We call those insulators, or very poor conductors of electricity. And then we have, so insulators, or poor conductors. And then we have these guys in the middle. And these guys in the middle are the metalloids. And some of these are what we call semiconductors, which means they have some characteristics of the great conductors and some characteristics of the insulators. And because in electronics, we use electrical signals to be able to tell our software what to do. So the electrical signals are what create the zeros and ones. We know that digital software, so digital environments, use zeros and ones to communicate. It's a binary system. And what really happens is the 0 number really just means it's a button that's in the off position. And a 1 is a button that's in the on position, because that's the only thing we can do with electronics is we can either turn off the electrical current or we can turn on the electrical current for different conductors. So if we have a chip and this chip has different paths coming out of it, so this is a circuit, these are multiple circuits. If there's no current going through the circuit, it's off. If there is current going through the circuit, then it's on. And that's the only way that we can control it for now. We're working on quantum computing, which will use many more systems, so it won't be binary anymore, but for now, that's the way it works. So because we're using electrical signals to tell things whether they're off or on so that we can create a binary system, we don't want things that conduct electricity too well, because that electricity could jump from one circuit to the other. We want things that can conduct electricity because we need to send that signal, but we don't want it to be super strong because we also don't want to create shorts within the chips themselves, because that would limit to how big we can make the chips. We can make chips very tiny with semiconductors because we know that they don't conduct electricity so well that it's going to create problems within the circuit. Without getting more technical, that's kind of what a semiconductor is. But that's why these are very important. And microchips wouldn't be the size they were. We wouldn't be able to carry phones in our pocket if it weren't for the characteristics of some of these particular metalloids. Any other questions?